Welcome to ScienceCover.com. Today we shall look at potential difference or voltage. We shall focus on what we mean when we talk about potential difference, how we measure the potential difference, and how it works in both series and parallel circuits. First, pause the video and complete the Do Now task. Let's check our answers to the Do Now task. Firstly, what is the rule to explain the interaction between charges? We know that like charges repel and opposite charges attract. How will a polythene rod and a perspex rod interact if they are both rubbed with a cloth? Polythene will gain electrons, so become negatively charged. Perspex will lose electrons, so will become positively charged. They will attract. How will two perspex rods interact if they are both rubbed with a cloth? Both rods will lose electrons and become positively charged, so they will repel. Let us begin by looking at what is meant by a potential difference. A potential difference can be thought of as the difference in charge between two locations. If these two plates have the same charge upon them, let's imagine they have 5 coulombs of charge on each plate, then we have the same charge on each plate. If we connect a voltmeter to each plate, the voltmeter will compare the charge difference between them. And since each plate has the same charge, this voltmeter will tell us that there is no potential difference. It will read 0 volts. If I place a wire between these two plates, then no current will flow as we have no potential difference and no charge difference between the plates. Now let us change the situation slightly and give one of the plates, let's say the right-hand plate, 10 coulombs of charge. Now I have a different charge on each plate, so if I connect my voltmeter to either plates, it now tells me that there is a potential difference. There is a difference in charge. So the voltmeter will read a number. Let's imagine it tells me that there's 2 volts. What this now means is if I connect a wire between the two plates, electrons will want to move from one plate to another, so a current can flow from the more positive plate to the less positive plate. So in this case, a current will flow from the 10 coulombs towards the 5 coulombs. Now a battery or a cell will make use of this rule that current wants to flow from a more positive to a less positive surface. And if we look at a battery, one side of the battery should be positively charged and the other side negatively charged. So if we connect these two sides with a wire, the electric current wants to flow from the positive to the negative. Electric current will always flow from a more positive potential to a less positive or a negative potential. Voltage allows current to flow through materials. A large voltage allows it to flow through a poor conductor or jump a gap. Air is a poor conductor. Charge can build up in the clouds as air currents move over each other. This creates a potential difference. So in this diagram, we can see that there is no charge on the ground because it is neutral. However, air moving in the air has transferred electrons to the clouds and it's built up a charge of 500 coulombs. Now 500 coulombs charge difference is not a large charge difference when we have a poor conductor like air. So it means that no electric can flow from one place to another. However, if the process continues and charge builds up in the clouds till we reach high voltages, so a large charge difference, then it means the electrons now have enough energy to jump the gap. So imagine the clouds have gained a 500 million coulomb charge and the ground is still neutral at 0 coulombs. This is now a large voltage difference, and electrons have now enough energy to jump the gap. Now pause the video and complete task 1. Let's check the answers to task 1. A, we have no potential difference. This means that no electric current will flow. In B, the current should flow from the 5 coulombs to the 0. In C, the current should flow from the 10 coulombs to the 5. In D, the current should flow from the 15 coulombs to the 5. In E, it should flow from 0 coulombs to -5. In F, it should flow from the 10 coulombs to the -5. In G, the current should flow from the 500 million coulomb cloud to the ground. And in H, it should flow from the ground to the -500 million coulombs cloud. Let's look at how we measure potential difference. Potential difference can be measured using a voltmeter. The symbol for a voltmeter is shown on the screen. In order to measure potential difference, the voltmeter must be connected before and after the component that we're looking at. This means that the voltmeter must be connected in parallel to a component. If we want to measure the potential difference across the cell, then we connect our voltmeter to either side of the cell. It will then measure the potential or voltage difference between each location. If we want to measure the potential difference of the bulb, then we must place our voltmeter with a connection either side of the bulb. This will measure the potential or voltage difference before and after the bulb. Now pause the video and complete task 2. Let's check our answers to task 2. What is the name of the device used to measure the potential difference? A voltmeter. Sketch the circuit symbol for a voltmeter. It should be a circle with a V inside it. Place a voltmeter on the circuit to show how we can measure the potential difference of the cell. The voltmeter must be connected either side of the cell. Add a voltmeter to show how we can measure the potential difference of the bulb. The voltmeter must be connected either side of the bulb. Let's look at how potential difference works in a series circuit. A series circuit is one where the cells, the wires, and all the other components make one simple loop. In a series circuit, the same amount of potential difference must be put into and lost from the circuit. So let's imagine we place in 6 volts into this circuit from the cell. Then that 6 volts will be carried by electrons around the circuit to the bulb, and as we only have the one bulb, that bulb must lose all 6 volts. In a series circuit with 2 bulbs, we take our 6 volts that is coming from the cell, and that 6 volts must be lost in the circuit. But now we have 2 bulbs. Assuming they are equal in resistance, it means that the voltage will be shared between the bulbs. So we lose 3 volts on each bulb. In this case, we have 3 identical bulbs. So again, if we take our 6 volts, we now have to share that 6 volts between 3 bulbs. So we will lose 2 volts on the first bulb, 2 volts on the second bulb, and 2 volts on the third bulb. In each case, we're always losing the same amount of voltage as what we put into the circuit. If the bulbs have a different resistance to each other, then it means that the voltage will still be shared between them, but unevenly. So for instance, if our 6 volts from the cell is placed into the circuit, and the first bulb and second bulb take 3 volts and 2 volts, then it means that we only have 1 volt left over, so this must be used on the third bulb. In this case, the bulb with the highest resistance will be the first bulb. It's got a higher resistance, and so it takes a larger share of the voltage. The bulb with least resistance will be the third bulb, and that takes the lowest share of the voltage. Now pause the video and complete task 3. Let's check our answers to task 3. We had to calculate the missing voltages. So for A, we should have had V3 as 6 volts. For B, V4 was 4 volts. For C, V3 was 8 volts. And in the table, the missing values were V4 was 1, V1 was 15, V4 was 4, V1 was 9, V2 was 2, V2 was 1, and V3 was 0.3. Let's now look how potential difference works in a parallel circuit. In a parallel circuit, the voltage is the same along each branch. Let's look at why this is. Imagine we have a cell and 2 bulbs in parallel, and the cell produces a potential difference of 5 volts. Any electron leaving the cell will have 5 volts. When it reaches a junction, it can only take one route. It can either pass through the center of the circuit, or it'll take the lower loop and go around the bottom. Let's assume that our electron takes the central route. When the electron reaches the bulb, it is carrying 5 volts, and it must lose this 5 volts of potential difference. So we will have 5 volts lost on the bulb in the center of the circuit. The electron then must complete the circuit and return to the cell. At the cell, it can pick up another 5 volts potential difference. And let's imagine this time the electrons are taking the route around the bottom of the circuit. Again, there is only one bulb on this path, so the 5 volts must be lost on that one bulb. So V3 will also give a reading of 5 volts. And then the electron must complete the circuit by returning to the cell. Now that's left us with a cell producing 5 volts of potential difference. The bulb in the center of the circuit is losing 5 volts on V2, and the bulb at the bottom of the circuit is losing 5 volts on V3. So each branch has the same voltage as the initial voltage from the cell. If we add a third branch to the circuit, the same rule will apply. So our 5 volts from the cell will see us have 5 volts on the first bulb, the second bulb, and the third bulb, as they're all wired in parallel. If a branch has multiple components, then the voltage is shared between those components. So again, let's assume we have 5 volts coming from the cell. The first and second loops in this circuit only have one bulb, and that means that in each case, electrons will only pass through one bulb and lose all 5 volts. But any electrons that travel the third loop are passing through two separate bulbs, so they must lose all 5 volts over the two bulbs. So this is going to split the voltage between the two bulbs. Now pause the video and complete task 4. Let's check our answers to task 4. Which of the following equations shows the relationship between V1, V2 and V3? Well, V1 is equal to V2 and that's equal to V3. Complete the table with the missing voltages. For the first one, V1 should be 6 and V4 should be 3. In the second one, V1 is 4 and V3 is 2. In the third line, V2 is 9 and V4 is 6. In the fourth line, V in should be 5 and V1 should be 5 and V2 should be 5. And in the last line, V in should be 1.2, V1 should be 1.2, and V4 should be 0.6.